Hello everyone, I'm Jing Xing Lim, a final year PhD student from Singapore University of Technology and Design. The title of my paper is Blockchain-Based Mechanism Design for Collaborative Mathematical Research. This presentation is done for the 2022 IEEE International Conference on Blockchain and Cryptocurrency. This is a joint work together with Barnabé Monnot from Ethereum Foundation and Georgios Piliouras from Singapore University of Technology and Design. So suppose that in the situation where you have some partial proof or partial result of an open problem that has been unsolved for years, I believe that most of us will be reluctant to share our partial result immediately and would rather share only after we have completed result. However, suppose that there are some sort of decentralized collaboration among researchers, there will be progress in the area they are working on. We'll take a look at some of the examples that's moving towards this direction. So I believe that most of us, when we encounter some problems in programming or mathematics, we will head over to Stack Overflow or Math Overflow to see if there's someone else who has the same problem as us and to see whether the problem has been resolved. Otherwise, we will post our queries via the platform, and usually it will take just days, sometimes within a day, or at most weeks to have our question answered. As a result, we can make progresses in our work through the help from people who we do not know in person. Next, the Polymath project is a project initiated by Tim Gowers, a British mathematician whose goal is to have a block format platform to allow mathematicians to work together by sharing their partial result. They have since published 4 to 5 papers on difficult problems in number theory. And lastly, we have ProofPeer. So ProofPeer is a project that aims to let mathematicians or computer scientists to formalize mathematics collaboratively through the use of interactive theorem provers or proof assistant. So why are they all doing this? So there are two main goals that can be achieved, or two main benefits that can be achieved. So first, difficult problems can be solved together. So for example, in the Polymath project, they have solved several difficult problems through this platform, through this Polymath project platform. And problems can be solved faster. That's the second benefit of having such collaboration. For example, a clear example will be through Stack Overflow and Math Overflow. Whenever you have problems, you'll head over to there and ask the question accordingly. And through the answer from someone else, that you are able to progress in your work. Despite these efforts that we have seen in our previous slide, there are still reasons why we choose not to share our partial results. We will take a look at some of the possible reasons. First, there is no feasible platform to share our partial results safely. We are afraid that people may take our work, complete it, and take full credit without acknowledgement. Second, there is no incentive for sharing partial result immediately. Suppose there are some sort of prize money for solving some open problem, having others copying our partial result without acknowledgement will in fact de-incentivize us from sharing our work. And lastly, reviewers may be reluctant to review partial work as they may not want to waste their time on results that are incomplete. So, how can we address these issues? In our work, we will show how we can use blockchain as a medium to tie collaborators. And why we believe so? First, decentralization allows provers and reviewers to contribute collaboratively in a decentralized manner. Second, timestamp verification will record all contributions from the authors accordingly. And lastly, with the use of smart contract, we are able to implement incentive mechanism that will distribute rewards, if there is any, accordingly and appropriately. This brings us to the next point. We will also introduce a proof of concept of how an incentive mechanism can distribute reward based on ability of the provers and the difficulty of the partial result. And lastly, to incentivize reviewers to review partial progresses, we will introduce an incentive debate system that provers have to put a stake for every proof presented so that reviewers can challenge them and possibly earn the stake. Reviewers has to also put a bounty for every review that they have provided so that the provers have the chance to rebut and possibly win the bounty as well. This is the overall summary of our proposed blockchain architecture. It consists of a data layer, which describes what data to be recorded, a client layer, which describes what information to be presented, and lastly, an incentive layer, which describes what data to be rewarded. We will take the next few slides to go through each layer one at a time. First, the data layer. A contribution can be from a prover or a reviewer. A prover will contribute through his or her proof, and a reviewer is through his or her question or review. Note that this question need not be addressing to a proof itself. So it can be just a question or a statement detailing an open problem. We need some form of storage system to store this data, be it a proof or be it a question itself. So as we want the whole system to be decentralized, every contribution will be stored in some form of decentralized storage system, for example, IPFS. After that, all necessary metadata, including the hash address of the contribution, will be recorded in the blockchain via a smart contract. We call it contribution registry. Next, the client layer. In this layer, a plugin text editor, something similar to Google Docs, can be implemented. This is to show the current proof progress, and reviewers can pinpoint the specific area of interest within the text. Subproof network will be presented to show the current stage of progress, which we will discuss more later. Note that this subproof network will be important in understanding the incentive mechanism, which we will describe later as well. A decentralized rating review system can be implemented as well to rate scores such as like novelty scores, simplicity or difficulty scores, relevance scores, similar to the scores that reviewers currently is providing during conference for their reviews. Lastly, the incentives layer. Incentive contracts are smart contracts that implements incentive mechanism once the whole proof has been completed. So the goal is to distribute tokens or reward, if there's any, appropriately to contributors through the allocation rule of the incentive mechanism. We will also have an NFT sublayer whose main goal is to keep track or keep digital representation of the work and its broader linkage with other works. Other than that, ownership of the NFT mathematical result can be transferred from one to another through sales. In some NFT marketplace, similar to how the sales of all of the popular digital works that we have been seeing ongoing recently. And portion of each of the sale can be taken and distributed to the authors of the work via the same allocation rule from the incentive mechanism as a form of remuneration. So it is important to show that such incentive mechanism does exist so that, number one, reviewers will be incentivized to review. Then number two, provers will be willing to share their partial result ASAP. So in the next few slides, we will go through a proof of concept of how such incentive mechanism can work. For our first goal of incentivizing reviewers, we introduce an incentivized debate system. Once a proof has been presented, the debate will start. Each debate will consist of some fixed L challenge rounds. So our analysis will work on the case when L equals to 2. So in this incentivized debate system, for each proof, it will come with a parameter set theta, so we can ignore the superscript u because we are working on just one proof itself, which comprises of rewards, which represented as R0, R1, R2, for the provers to earn, stakes for the provers to stake for each of their proof, which represents sigma 1, sigma 2, and bounties for every questions and reviews from the reviewers, who represent beta 0 and beta 1. So, however, instead of having a committee to decide whether the result to be accepted or not after 2 rounds of debate, we will have require the prover to provide a formalized proof to end the process. So what do I mean by formalized proof? As formalized proof is not the main topic of the talk, I'll keep it brief. We just need to know that formalized proofs are mathematical proofs written as codes, okay, programming codes, so that the proofs can be automatically verified by computer. So back to our incentive mechanism. I'll suppose a prover at the start have some claim of a proof, decide whether to post or not to post. Suppose it do not post, of course he will not get any reward. Reviewer, same for the reviewer. So however, if he decide to post, it comes with a stake of sigma 2. We will count the round in a descending order. So after which, the reviewer will decide to challenge or not to challenge. Of course, if decide not to challenge, the reprover will get the reward of R2. Okay, so reward associated with round 2. And if you decide to challenge, the reviewer need to pay a bounty or come up with a bounty together with the review or the queries that he have of beta 1. At this point, the prover will know whether his or her proof is formalizable. You will then decide whether to reply or not to reply the reviewer. Suppose it not to reply, you will lose the stake that he initially given over here, sigma 2. However, if he decide to reply, he need to put an additional stake together with his reply, be it a proof, be it an argument of sigma 1. After which, same, reviewer need to decide whether to challenge or not to challenge. If decide not to challenge, you will get the reward associated with round 1 together with the bounty that for his initial challenge. And if he decided not to challenge it, you need to pay additional bounty of beta 0. So at the end of 2 rounds, if the formalized proof is given by the prover, you get a reward of R0, beta 1 and beta 0, which is all the bounties and the reward associated with round 0. If you are unable to do so, he will lose all his stake and it will be earned by the reviewer itself. Based on the system I described, there's a game theoretical result by Curry in 2021 that mentioned that the game designer, or we can adjust the parameter set theta such that every prover or prover I will only post his claim of the proof if his or her confidence, we represent a PI, is greater than or equals to pi star, which represents some form of minimum threshold confidence. And this pi star is a function of all the reward stakes and bounties. So what do I mean by that? You can adjust the reward, the stake, and the bounty accordingly such that certain pi star has been reached. And because of that, one of these equilibrium type can occur. So either you can set it as a high threshold confidence or high pi star, medium pi star, or low pi star. So for high pi star, it will be difficult. It's a type 1 equilibrium where it will be difficult to accept, and reviewer will, in this equilibrium type, reviewer will always challenge the initial claim, but only challenge the rebuttal with some probability. On type 2, where it is moderate to get accepted, the reviewer will challenge the initial claim and rebuttal with some probability instead of a so-called compulsory challenge for the initial claim as seen in type 1. As for type 3, it will be the case where it is easy to get accepted. So in this case, in this type, reviewer will never challenge the initial claim or rebuttal. You can think of this as sort of like an archival system that where people just post their result over there. However, this game theory result does not take into account of a collaborative setting. So this is where we will improve on this result and share with you what if this kind of setting, this kind of result if we implement it in a collaborative setting. For our second goal, we want to incentivize provers to share their partial progress ASAP. We do not want to be in this situation where the prover believes he has contributed more than 50% of the overall proof and expecting to get at least 50% of the rewards, but end up just getting 10% of the reward. Thus, it is important for us to have an incentive mechanism that distribute rewards appropriately. Before we go to the analysis, we will use directed acyclic graphs, ducts, to represent proof. In this representation, every edge represents a subproof. For dotted edge, it represents incomplete subproof, and for solid edge, it represents completed subproof. Over here, we have a single dotted edges connecting two nodes to represent an open problem. Suppose someone come up with an open problem, this is how we represent using duct. When an initial subproof has been presented, the single dotted edge will turn into the duct that we have seen over here. So when H0 represents the initial subproof that someone have contributed, and the M0 parallel edges represent the required incomplete lemmas assumed by the initial subproof 0 in order to complete the whole proof. Note that having just one dotted edge turn it to solid is not enough. We require all these lemmas, okay, lemma 1 all the way to lemma m0, to be completed and hence turn solid in order for the whole proof to be solved. We will look at our first main result, which focuses on the subgraph with only the parallel edges. So this result tells us that suppose these two conditions hold, every prover will follow PPS policy, which means partial progress sharing, which means that every prover will share their partial result immediately. And for any subset of parallel edges from these M0 edges, so be it the whole thing or just a subset of it, the game designer can make one unique subproof with the highest weightage, which I will elaborate more later, such that every prover will herd together and work on that unique subproof. So now I will elaborate more on these two conditions and what do I mean by weightage. Recall that from the previous game theoretical result, the game designer can fan the rewards, stakes, and bounties such that it will be difficult, moderate, or easy to get accepted. So yeah, the first condition requires that this game designer chooses one of these type to hold for each every edges over here. Next, the second condition requires the game designer to have some sort of ordering for this parallel edge. So what do I mean by that? So we can write V is less than U, or you can think of it as V having less weightage than U, if and only if SV multiplied by theta V is less than SU multiplied by theta U. So SV, SU represent the simplicity of subproof V and U respectively. So let's break it down first. What do you mean by multiply? If multiply means scalar multiplication component wise. So this means SV multiplied by theta V represent SV multiplied by RU, R0V, R1V, R2V, and same for all the sigma, all the beta component wise. And same for all the U. Then after that, this less than is comparing component wise as well. So over here, I write it more explicitly. SV multiplied R0V is less than SU multiplied R0U, and same for all the R1, Rs, all the sigma, and all the beta. So suppose these two condition holds. Okay, suppose the game design the fine-tune or set the parameter set such that these two condition holds. Every prover will follow PPS policy, will share their result immediately. So, and every prover will work on the unique subproof U star, which is the argmax of U, SU, and theta U, which means herding. So this one represents sort of the highest weighted edge of the rest. Yes. So with that, we finish the part where we look at the parallel edge. Next, we look at what if we add in the additional initial subproof. For our second main result, we look at the entire duct where the initial subproof 0 is added to the parallel edges. We will see what are the conditions required for the provers to be incentivized to share this or any initial subproof when they found one. So similarly, the first condition will be to suppose that game designer set up the parameter set such that one of the equilibrium types, more difficult, moderate, easy to get accepted, one of these type to hold for every edges, including 0, and this inequality holds. So what does this inequality say? So theta 0 is greater than or equals to the max of alpha, max of all the parallel edges, okay, of alpha SW0 multiplied by theta W. So alpha represent the best prover inner ability, so like a mathematical ability as compared relative to all provers. And SW0 represent the relative simplicity of subproof ZW and 0. Okay, so same thing, the multiplication means component-wise multiplication. Okay, so to elaborate, to understand this better, so maybe I give some examples. So for example, if the best prover's ability increases, alpha will increase. Hence, more weightage will be put towards, okay, in terms of rewards, stake, and bounties will be allocated to the initial subproof 0. Similarly, if the simplicity of the subproof in the parallel setting, like the max out of all the parallel setting, the simplicity of them increases, which means subproof 0 is more difficult, more weightage will be assigned to subproof 0. Okay, so if the game designer scales the reward such that reward, bounty, and the stake such that these two conditions holds, then every prover will share their initial subproof 0 if they have found one immediately. So to summarize, for our second goal of incentivizing provers to share their partial progress immediately, main result to provide us condition. Okay, main result to provides us condition for the reward, stakes, and bounty to incentivize every prover to share their initial subproof once they have found one. And main result 1 will look at the parallel edges and further provides us the condition to structure the reward, stakes, and bounty for the rest of these parallels, these subproof that arranged in a parallel manner. To conclude, our contribution include a blockchain architecture for some sort of collaborative decentralized conference. Although our work discusses the system in the field of mathematics, we believe that this can be expanded to other fields of sciences as well. We also provide a proof of concept of an incentive mechanism which can be deployed using smart contract to incentivize provers to share their partial progresses immediately and for reviewers to review. So what if we want a system that only accepts formalized proofs instead of pen and paper proofs? In our previous work, we described how such a system would work. And for one of our future works will be to develop a DApp for this system so that we can evaluate its effectiveness and also the effectiveness of the incentive mechanism. So with that, I would like to thank you for listening. So thank you.